Hi, I'm Matt, and I'll be showing you how to solve a physics problem. So here's our question. An astronaut on the moon has a slingshot. He launches a moon rock at an angle of 60 degrees with a velocity of 20 meters per second. He prepares to launch a second moon rock at an angle of 20 degrees. Assuming that the initial velocity of the second moon rock is also 20 meters per second, how much later would the astronaut have to launch the rock in order for it to hit the first rock while it was still in the air? How far away from the astronaut will they be when the collision occurs? Just some extra information, the acceleration due to gravity on the moon is 1.62 meters per second squared, instead of 9.8 meters per second squared like it is on Earth. So let's start with what we know. We know that the constant vertical acceleration due to gravity will be negative 1.62 meters per second squared. We also know that there is no horizontal acceleration. We also know the initial velocity of the first and the second rock. In order to calculate its vertical velocity, we will multiply 20 meters per second times the sine of 60, which will result in 17.32 meters per second. And doing the same thing for the vertical velocity of the second rock, except replacing the 60 with 20, we'll get 6.84 meters per second. Likewise, 20 meters per second times the cosine of 60 degrees is 10 meters per second. And the horizontal velocity of the second rock is 20 meters per second times the cosine of 20 degrees, which is 18.79 meters per second. We also know that when the rocks collide, they will have the same horizontal and vertical displacement. So the displacement is the initial velocity times time plus half the acceleration times time squared, which can also be expressed like this. If t is equal to the amount of time since the first rock was shot, and d is equal to the delay between the launch of the first and second rock, both t and b being measured in seconds, then for the first stone, the horizontal displacement will be equal to 10 meters per second times the time, and for the second stone, it will be 18.75 meters per second times the time minus the delay. So in order to calculate the displacement of the second stone, we are going to subtract how long the astronaut waited from the total time that we have been measuring. These same equations can be used to express the vertical displacement of the rocks, and we need to keep in mind that the force of gravity is applying an acceleration of 1.62 meters per second squared downwards, which means if we substitute in our values for the first stone, we get 17.32 meters per second times time plus half of negative 1.62 meters per second squared times time squared. And for the second stone, we'll get 9.84 meters per second multiplied by time minus the delay plus half of negative 1.62 meters per second squared multiplied by the time minus the delay squared. Because we know that at the time the two rocks collide, they will have the same horizontal and vertical displacement, that means that at the time, the horizontal displacements and the vertical displacements will be equal, which means that we can just substitute these values to give us 10 meters per second times time equals 18.75 meters per second times time minus delay. That also means that 17.32 meters per second multiplied by time plus half of negative 1.62 meters per second squared times time squared is equal to 9.84 meters per second times time minus this delay plus 1/2 negative 1.62 meters per second squared multiplied by times minus the delay squared. And so you could see what we're doing is we are setting their displacement equations equal to each other because we know that they are the same. So now we can arrange this equation to d is equal to 0.46t. You could technically arrange either equation to solve for a variable, but this one is just a lot easier to do. So after that, we can use substitution and substitute 0.46t for every d in our equation, which means that only this side will be affected since that is the only side with a d in it. And once we solve this equation, we're left with t is equal to 20.92 seconds. So now that we know that, we can substitute the value of t back into the equation d equals 0.46t, which results in d equaling 9.63 seconds. This means that by launching the second rock 9.63 seconds later, the two projectiles will collide 20.92 seconds after the initial shot. Now, knowing the time at which the two rocks collide means that it is possible to calculate their displacement at that moment. In order to do this, we can substitute the value of t back into the equations for the first rock's horizontal and vertical displacement. Again, you can also use the equations for the second rock, but that would also mean that you have to factor in the delay. So once we do these, we get that it has moved 209.24 meters horizontally and 7.77 meters vertically. So now that we know this, we could use the Pythagorean theorem in order to calculate how far away from where the astronaut is standing it actually was. So all we have to do is make a triangle like this. So our stone would be at this point over here, and we know the height and we know how far it has traveled horizontally, which means that we can calculate this distance. And so we just do the Pythagorean theorem and we'll get that it is 209.39 meters. So our final answer is that the second rock should be fired 9.63 seconds later, and that the collision will happen at a distance of 209.39 meters from where the astronaut is standing.